I have spoken about the property strangeness of a quark, but I haven't explained it fully. I've explained nothing. Yeah, to be honest, I've explained nothing. So let me explain what strangeness is. Now, strangeness as a broad way is a very complicated concept, but for simple uh, understanding, strangeness is nothing but the measure of strange quark content. Yeah, I repeat, strangeness is nothing but the measure of the strange quark content in a particle. That's all. I mean, there are six type of quarks, and this classification is based on flavors, quark flavors, which we will learn in the coming few minutes. And one of the quark is known as a strange quark. So, a particle, the strangeness of the particle is the degree or is defined by the number of strange quarks present inside that particle. That is defined as the strangeness because strange quark is the only quark which has a non-zero strangeness. I repeat again, strange quark is the only quark which has a non-zero strangeness other than all the five quarks. Right. So as you can see, the up quark has a strangeness of 0, down quark has a strangeness of 0, but a strange quark has a strangeness of -1. Now let's move on to something which is quite interesting. I mean, all of these topics are interesting, but this thing, I mean, honestly fascinates me. Okay, so quarks are the fundamental entities, and quarks uh, constitute, uh, I mean, are the building blocks of hadrons, right? Let's go back to a previous slide, this slide. Here I have written the Pauli exclusion principle. I mean, let me read out the statement which I have written again. For particles having a half integral spin, no more than one similar particle can exist in the same quantum state, two similar quarks, same quantum state. This means two similar quarks cannot exist in the same particle. Cannot. Right. So let's look at the structure of a neutron or proton. Neutron has one up quark and two down quarks. So this contradicts my statement there, which was that two similar quarks cannot exist in the same particle. But a neutron is a stable particle and it has two down quarks. How is that possible? I mean, two down quarks. Here in proton we have two up quarks. My bad. Sorry. Yeah. So we have two up quarks. How is that possible? This suggests that there must be some other property, some other aspect which differentiates these two down quarks. This is the down quark, this is the down quark. There must be some property which differentiates these two down quarks. There must be some property which differentiates these two up quarks. Yes. And this property is described as color, the quark color. We now move on to our next topic, which is the quark color hypothesis. It is an additional property associated with quarks which distinguishes quarks with each other and preserves the Pauli exclusion principle. Right. Now, so let's move on to quark color hypothesis. But before that, I would like to just state that the charge, the spin of these particles, they all arise due to the presence of quarks. Right. Now, let's move on to the quark color hypothesis. So, I've made a slide about that. Yeah, this slide. Now, color theory, as I already stated, was developed to preserve the Pauli exclusion principle. That is, to overcome this violation of Pauli exclusion principle, which was visible in case of neutron and in case of proton. For example, let us take the example of electronic charges. So, charge is a property of an object. When positive and negative charge come together, they create an electronically neutral whole. Charge is a property that can manifest as in positive and negative. Quark color hypothesis is similar to this concept. Now, quark color hypothesis states that color can manifest in 6 different ways. The 6 different ways are red, green, blue, anti-red, anti-green, and anti-blue. These colors have nothing to do with visual colors. They are not classical colors. I mean, I've written red. This doesn't mean the color of the quark is red. No. This doesn't mean the color of the quark is green. This doesn't mean the color of the quark is cyan. This is cyan color. Cyan. It is anti-red. This is magenta. It is anti-green. And this is yellow. This is anti-blue. Right. This doesn't mean that it is yellow in color. No. It has nothing to do with physical colors. It's just a naming convention. Just a naming convention for ease. As we were discussing, uh, the naming convention is just for ease. Yeah. So any quantum property, this Q, can be denoted by suppose X, Y, Z. But why color was chosen as the distinguishing factor? It was chosen so that we can better understand. It was chosen so that we can better understand how these colors come together to create hadrons. To understand how these colors come together to create hadrons. Yeah. So let's draw an analogy connecting the quark color hypothesis to something we to something we already know. So what is that thing? Scattering of white light. Yes. We know that white light comprises of three primary colors. These are RGB, red, green, and blue. And these three colors are the three primary colors existing in the nature, and all other colors are derivatives of these colors. Derivatives of RGB. Derivatives of, combinations of RGB. So, uh, just as these three colors come together to create white light, likewise, all hadrons, likewise, likewise, all hadrons are, sorry, sorry, all hadrons are, sorry again, sorry for the inconvenience. All hadrons are supposed to be colorless. They come together in such a way that they means here the quarks. They come together in such a way that their color properties will either be in equal proportion or they will, I mean, the colors will, I'll erase they, or will totally cancel each other out, making the hadron colorless. So we draw an analogy for this from the scattering of white light, which we read earlier in our school days, right? Uh, For example, a baryon has three quarks, each having the color red, green, and blue. But the baryon is colorless. Let's take a meson for example. Meson, which is QQ bar, quark and antiquark. So two quarks, red and anti-red. So the meson will be colorless again. Right. So all naturally occurring hadrons are colorless. Uh, this property is intrinsic to quarks only, not valid for for other domains. This quark color hypothesis explains that why certain type of hadron particles having certain number of quarks aren't found. I mean, uh, this limits the combination of quarks and hadrons. Yeah, certain number of particles with certain number of quarks. I mean, all type of particles with a varied number of quarks are not found. Now, uh, let's consider another example. We have a hadron with two quarks, but it's not a meson. So no antiquark. Such a hadron is not possible to exist because two distinct colors, fundamental colors from RGB cannot cannot make the hadron colorless. Yeah. That's why two quark and four quark combination are non-existent in nature. Thus, this hypothesis explains the properties of these particles pretty well. Hadrons that are colorless don't exist. So, as you can see in the diagram, uh, these two down parts are not alike. The color property actually differentiates these two down parts. Similarly, the color property distinguishes these two upwards. Yeah, so the color property actually differentiates these two down quarks, and there, in case of a proton, the color property distinguishes these two up quarks. Now, let's move on to the next topic. But before that, I would like to discuss that as I already said that the color property is a very intrinsic property and is uh, confined to the domain of quarks only and doesn't apply to the macroscopic objects. The idea of color is intrinsically linked to the strong force itself. Yes, the idea of color is intrinsically linked to the strong force itself. Quarks are attracted to each other due to the strong force. Let me write it. So, quarks are attracted to each other due to the strong force. The strong force is very much dependent on this color property. This is dependent on the color property. As a result of this, uh, but before that, let's draw an analogy to better understand the dependency of strong force on the color property. The strong force is dependent on the color property in the same way. Let's suppose the electromagnetic force is dependent upon the charge property. Let me repeat again. The strong force is dependent on the color property in the same way uh, in the same way Electromagnetic force is dependent on the charge property. Yeah. That is why strong force is also called the color force. Right. As of today, we know many more types of quarks. So we have another classification of quarks on the basis of flavor. Yeah, flavor means something sweet or salty or sour, but that's not the case. Uh, it's just a representation like color. Now, honestly speaking, I don't have any idea who came up with the concept of flavor of quarks, right? But it is how it is. Like, so, flavor, flavor tells us whether a quark, whether a quark is up, down, strange, charm, top, or bottom. Yeah, this top quark, as we learned from the history of particle physics, was discovered later, found in heavy particles at high energy that were very unstable. So we have six different flavors, six different tastes, six different quark particles. These are the six different quark particles: up, down, strange, charm, top, and bottom. These are as evident in the standard model: up, charm, top, down, strange, and bottom. Yeah. So, the manifestation of the quark flavor is obviously a mathematical approach, but today's lesson is purely theoretical. So, I'm not getting into rigorous mathematics. Uh, yeah, that's why we can't go there. Now, keeping aside all the fundamental, all the keeping aside all these theoretical ideas of these fundamental entities consisting hadrons in different proportions coming together, experimentally none of the quarks have been actually been isolated. This is a very important topic. Quark isolation is still hypothetical. But you would ask me that in a nuclear reaction, suppose a nuclear fusion reaction, we can disintegrate a nucleus. Yes, if we bombard it with a neutron. So why can't quark be isolated from a neutron or a proton, right? So there is a reason why quark cannot be isolated. Like in half a century of a time, scientists have tried numerous times, numerous efforts. Yes, but they are unable to isolate quarks from baryonic matter. Uh, this brings us to the topic of quark confinement. Yes. So inside a hadron particle, a baryon has three quarks. So baryon, three quarks, and these quarks are attracted to each other due to strong interaction. So force existing in quarks is due to the color property, right? We learned about the quark color hypothesis. So the force existing between quarks is due to the color property. Yeah. Uh, Now, as we were discussing the history of particle physics, we came across a particle known as gluons. Gluons, right? Gluons is a Gluons are bosons, right? So, among these quarks inside a baryon, inside a hadron, there exists exchange of particles which are known as gluons. So strong interaction is nothing but exchange of gluons. Due to the exchange of these gluons, all the forces in these distances, as observed, the strong interaction is the strongest force in the distances uh, of quarks. Exchange of gluons makes the strongest makes the strong interaction the strongest force possible. It holds together the quarks. Let us take an example. Let us consider that there is a bond or an attractive force which can be replicated by a spring, right? It can be replicated by a spring. Yeah, this diagram. Suppose this is a spring. Yeah. So the bond or the attractive forces between the quarks are represented by a spring. So in this case, for a proton, the three quarks up and down are attached to each other using the spring. Yeah. So as we extend the string, as we extend the spring, the force, the restoring force of the spring increases. The more we pull the spring apart, restoring force increases. More we pull the spring apart, the more uh, the force to bring it back increases. In real life, in real life, such a spring would definitely break. I mean, in real life, we cannot stretch a spring. I'm sorry. In real life, we cannot stretch a spring infinitely. We cannot stretch it infinitely. We cannot stretch it infinitely. At some point of time, it would break. It would disintegrate. But in this theory, as we as we exert force separating two quarks together, the force holding them back actually increases. So more we pull the spring apart, the more the force to bring it back increases. That's why it's extremely difficult to break a hadron particle. In real life, the spring will break, but here, if you try to break the spring using high energy externally, in real life, spring will, I'm sorry, break. But if we apply high energy like a nuclear reaction, where we bombard the hadrons by smaller particles like electrons, we may try to break it apart, but something unusual happens. So, what unusual things happen? Let me explain. The unusual thing that happens is as we apply energy energy to this entity, we cannot isolate them. What we create is nothing but a quark anti quark anti quark pair. Right. For example, we consider a neutron up, down, and down. So, we took the example of a neutron. So, we have a up quark, a down quark, and another down quark. And we bombard it with a gamma photon. So, we want to break apart the neutron. We want to break it apart. This is a neutron. Right? Yeah. So, the energy. So, what actually happens is that the energy of the gamma photon energy is used to create a quark anti-quark pair. Yeah. And reshuffling happens to create two different particles. So what actually happens is that up, down, and up. And here we have down, and the anti part and the anti quark of up is this, right? So reshuffling occurs, and this is nothing but a proton, right? And this is nothing but a pi meson. So when we bombarded the neutron. Yeah, we bombarded the neutron with a gamma photon, and and it created a proton and a pi meson. So quark anti-quark pair is created, but they do not interact. So there is no annihilation. So but they are rearranged to form new particles. That is a proton and a pi meson in case of a neutron. So when a neutron is bombarded with a gamma photon, a proton and a pi meson is obtained. This happens with all hadronic particles. I mean, all the hadronic particles, when bombarded with a smaller smaller mass particle, uh, two different, two new particles are created. So this happens to all hadronic particles, and this idea is called the idea of quark confinement. It is similar to that of magnets, I mean, when we cut a magnet, then we do not obtain separate north poles and separate south poles, right? When we cut a magnet, then the daughter magnet, I mean, the smaller magnet we obtain has a separate north pole and a separate south pole. So this is how we draw analogy from what we have learned earlier. So same thing happens with quarks. This is the idea of quark confinement. So now we are coming to the end of this lecture. Uh, let's again move back to the standard model diagram, which we yeah, this is where it is. Uh, in case of we are almost done with quarks. Just I need to speak just a few lines about leptons. Like leptons, like quarks, are fundamental particles, and I mean they are elementary in nature, and they also, like quarks, cannot be broken down into other smaller particles. This is the first generation of leptons. This is the second generation, and this is the third generation. This horizontal row, this row, in this row, all the leptons are charged. So this row is known as charged leptons. It includes the electron, the muon, and the tau. All these were introduced in the history of particle physics part, and these are neutrinos. They are leptons, but they are all neutral in nature. So they are neutral leptons. This is an electron neutrino. This is formed due to a reaction with an electron. This is due to muon, and this is due to tau. These are gauge bosons, these four. Gluon and photon are already mentioned. Z boson and omega boson are to be discussed in some other videos. And Higgs boson, I've discussed a few things about it while discussing the history of particle physics part. It is called the scalar boson. Now that's all for today's lecture. I hope you all enjoyed it to the fullest. I know I've made it a bit long, but I hope I've cleared all your doubts, and I hope I went into the depth of this topic. To please stay tuned for more such videos to come. Thank you.